Okay, this is trying to help you with your revision for the motion topic in paper 2 physics. So you should have a little booklet, and the idea of this is you fill in the booklet as I'm going through the video. So there might be bits that I tell you how to do, there might be bits that you have to then have a go at and do yourself. So you've got the bits at the top, which are the slides on here. And the bits at the bottom, there should be a space for you to write anything that you need to write. So can you fill in that little bit at the bottom with any answers to the questions? Okay. Right, to start us off, equations you're going to need for this topic. So there's a couple of equations you're going to need to remember and one that you're going to be given on your equation sheet. So first off, you're going to need displacement equals velocity times time. Now you might have heard of this being slightly different as distance, speed and time, but we're going to learn this one. Displacement and distance, we'll look at the difference between them, and velocity and speed, we'll look at the difference between them a little bit later on. But if you remember that displacement is velocity times time. Now again, you might have heard of it as velocity is displacement divided by time. Doesn't matter which way around you remember it, as long as you do remember it. Obviously then you might need to rearrange it as you get through. So displacement in meters, the symbol is S. Okay, you might think of S being speed, but it's not. It's the distance or the displacement. Velocity in meters per second with a V, and time, the lowercase t and an S as seconds for your units of measurement. Okay, next one. Acceleration is change in velocity divided by time. So acceleration first off is meters per second squared. Now this is because we're doing meters per second divided by seconds. So that gives us meters per second, okay? And we can shorten that down to meters per second squared. Right, as well as this, change in velocity. To find the change in velocity, we've got v minus u, so that's the final velocity, the speed you're going at the end. Take away the initial velocity, the velocity you're going at the beginning. So if something speeds up, you're taking away those numbers and finding out how much faster it's got. Divide that by how long it took and you work out how much faster it gets every second. Last one, this one's one that's on your equation sheet, okay, so you don't need to remember it. Now it's quite difficult though, so it's v squared minus u squared equals 2 times a times s. So with v being the final velocity in meters per second, u being the initial velocity in meters per second, 2 is just 2, a is acceleration in meters per second squared, and s being the distance covered. So this, I'll put a link in the description to some videos showing you how to go through this. We've done those in class, but if you want to go back through those again, if you're not sure about this, I would advise you do go back and have a look at those again. Because it's a difficult equation to look at, but if you take it step by step, it's really not as hard as it looks in the first place. Okay, so difference between distance and displacement. So this little diagram here is showing us this. So the blue line here at the top, that is showing us the distance. Okay, so that's the distance. Now basically the distance is, quite simply, just how far you've gone. Okay, so it's how far you go altogether. So if you imagine looking at a car, if you're driving a car, okay, and you look at how many miles you've gone at the start. Okay, so if your car's done 1,000 miles, or 1,000 meters to make sense with this, at the start of the journey, by the time you got to the shop, it had done 1,220 meters. Okay, so it's just how far you have gone, doesn't matter which way you're going. Okay, now displacement is this one here. Okay, so that is the displacement. Okay, so the displacement being the distance and direction, or it's the distance in a straight line from A to B. Okay, so from where you start to where you finish, or from start to finish. So if you measure a direct straight line on a map with a ruler, that's how far you've gone. Okay, it doesn't matter how you got there, it doesn't matter which way you went. Now, because it's got a direction as well, that's why we need this bit at the top. Okay, so you will always have like a compass at the top. And this will tell you which direction you've gone in. So if you have a look at this here, okay, we're going sort of this direction. So I would say that's probably going east. So you'd say 130 meters, and you would add on the end of that, ideally. Okay, you would add on the end of that east to make it a little bit better. Okay, that tells you which direction it's going in as well. Okay, so if we had to then measure the displacement, and we knew that 1 centimetre equals 5 kilometres. Now I'm going to do this on here, but you're going to need to do this in your actual booklet, and the distance is going to be slightly different because 1 centimetre on the screen is going to be different to 1 centimetre in your actual booklet. Right, so first thing I need to do, if your displacement is, as we've just said, the distance in a straight line from point A to point B, okay, or start to finish, we're going to draw a line from start to finish, like that. Okay, so in your booklet with a ruler, you draw a line from start to finish. Then we need to measure that line. So I am going to need a ruler, okay, and I'm going to use that ruler to measure the distance. So put it at the start, and oops, okay, put that over there. I'm going to measure how long it took from start to finish. So that is, I would say, 15 centimeters. Okay, so it's 15 centimeters from start to finish, but this is a scale, so 1 centimeter is 5 kilometers. So I know it's 15 centimeters start to finish. So I will do 15 times 5 kilometers. Now you might need to work this out as a scale. You might need to work out your scale. So you might need to work out how many centimeters or how far is 1 centimeter. Okay. If you're not sure with that, if you go and have a look at the videos I've got on here about vector diagrams, that'll show you how to work out a scale, how to calculate a scale. I'm not going to go through that on here. So again, if you're not sure how you work out a scale, go back to those videos on vector diagrams, have a look at those, and it should show you how you work out a scale. Right, anyway, so I do 15 times 5, okay, and if I do that, okay, I don't know if I can get a calculator up. So 15 times 5, and that will give me the distance I've got. And I'm going to do it on here because I want you to work out your own. So yours isn't going to be 15 centimeters, yours will be something completely different. Okay, and on the end of that, you're going to add on the direction. So if I look at where it's going somewhere in between north and east. Okay, so I'm going to put, it's going to go northeast. So whatever you get for yours, whatever you get, so you're going to get a different number here, okay, because you're going to measure something different, and then you're going to get a number in kilometers, okay. Right, moving on. So the difference between speed and velocity. So this comes on to thinking about back to scalar and vector quantities. We've just talked about scalar and vector quantities actually, because distance is just how far you go. That's not got a direction, whereas displacement has, and that's the difference between a scalar and a vector quantity. So speed in this case is scalar. So that means it just tells you how many meters you cover in a certain time. Okay, so how many meters in 1 second. Whereas velocity is a vector, so it has a direction as well as a magnitude. And that tells you the speed and the direction. So it tells you how far you've gone and which direction, sorry, how fast you're going and which direction you're travelling in. So if you look at these two examples at the bottom, if you're just looking at a speedometer, okay, 70 miles per hour, that could be going north, south, east or west. You don't know where it's going. If you look at an actual car moving, it will have a speed, so it might be 70 miles per hour going north, okay. So this comes on to something which is higher tier only, which is about the ability of something to go at the same speed while turning a corner, okay. So if this car is going 70 miles per hour and it turns a corner, if it's going on a motorway and it starts turning, gradually turning a corner, it's still going the same speed, but now it's going a different direction, okay. So things can change their direction and therefore change their velocity, but keep the same speed. This also allows things to accelerate round a corner without changing speed. Okay, so it sounds a bit strange that you can accelerate without changing speed, but think about it. Think about what acceleration is. Acceleration is change in velocity divided by time. Okay, so if acceleration is change in velocity divided by time, then if our velocity changes because our direction changes, then our acceleration must change. Okay, because we've got a different change in velocity, so the acceleration must change. Moving on now, we have the same sort of shapes which can confuse you to think these are the same things. But now we've got velocity time graphs. Okay. So what this is, basically we've got the same sort of shape graphs, but at the bottom we've got showing velocity instead of, oh, I've done all them wrong. Right, moving on now to displacement time graphs. You have a little mistake in your booklet, so you might want to change that. I think in your booklets it says distance on the bottom and time up the side. So you want to change that to displacement up the side and time along the bottom. So sorry about that, I will have printed off like that. Anyway, first one. So what's happening here, I'm going to try and show you this little boy at the bottom. So displacement is how far away you are from a certain point. So it's how far, in this case, the little boy is away from the wall. So we can measure that, and if we measure that every second, we will be able to plot that on a graph. That's what we're going to try and show. So with this one, if we measure the distance at 1 second, okay, there he is, okay. Second per second, again, it's that same distance away, and the third second and the fourth second and so on, because he's stationary. So he's not moving, he is stationary. On the second graph though, if you look what's happening, every time you're taking a point, it's further away from where he started. So every second, the boy is getting a little bit further away. So again, we take that first second, he's maybe 1 meter away. Second might be 2 meters away. Third second is 3 meters away, and so on, because he's moving at a constant speed or a steady speed, so a constant speed away from the wall. Now, if we made him go faster constant speed, okay, so rather than going like this, if he was going like that, that would increase the gradient of the line, because every second he'd be getting further away. If we made him go slower, so really moving quite slowly now, then again every second you're not moving quite as far, so the line wouldn't be quite as steep. Now if the boy was moving backwards towards the wall again, okay, then the line will go down because the distance from the wall is the opposite, is going the opposite way. Okay. Now last one. So this one's a bit trickier to show you, but if we think, right, the first second, again, quite close to the wall there. Second, not move much further away. Okay, third second, start moving a bit further away. So if you remember, first second to second second, we were kind of that distance. Okay, the next one, I'll show you a different colour. We're going to move much further. And then in the next bit, if you look on the graph, the next second, we're going to move much further again. Okay, the displacement's getting bigger every time. So we're going kind of 1 second, 2 seconds, 3 seconds. By the third second, fourth second, moving much faster because he is accelerating. Now the opposite of that would be obviously decelerating, and that wouldn't be, so it's quite tempting to think decelerating would be going like that. It's not. Okay, that's wrong. Decelerating, you're going to start off going much steeper and level out. Okay, because again, think about the gradient being the speed or the velocity. You're going a fast velocity at the start because it's steep. That's going to curve off at the end. Okay, next one. Again, I've left it like this time for you. This is going to be wrong, so you need to swap around your time and your velocity. Okay, I don't know why I didn't spot this before. Just make sure you do that because it will always be this way around. You will always, if you think about what these graphs mean in terms of variables, your time is your independent variable. That's the thing that you're choosing. You're taking a measurement every second or every 5 seconds or every minute or whatever. So time is going to be on the x-axis because the independent variable always is, and the velocity, the speed, is going to be up the y-axis because that's what you're going to measure every second. So in this first one, now they look the same as these last ones, but this is not stationary. Think about what's happening. So the velocity is up here. If it was stationary, the velocity would be 0, so it'd be down there, but it's not, it's there. So he's moving at a constant speed away, same as with the first graph. So if it's a straight line like that, it's a constant speed. The second graph, okay, we've got actually the same as this graph here, is accelerating. And it's hard to show you with the speeds, but if you think about it, every second, looking at how fast it's going, first second, I don't know, 5 meters per second, second second, 10 meters per second, third second, 15 meters per second, but he's accelerating at a constant rate, okay? Or we'll call it constant acceleration. So every second in that example I just gave you, the boy was moving 5 meters per second faster, okay? Now on the last graph, that is not constant because it's curving up. And again, like on the distance time graphs, the steeper, the faster. So steep, really like accelerating really quickly. Lower, accelerating at a very low rate. So on this, the acceleration is increasing. Now, if something was decelerating, all you need to do is show it going down. Down this time doesn't mean backwards. Okay. For something to go backwards, what it would need to do is have a negative velocity. Because negative velocity, so if you look at this graph, for example, even down here when it's going backwards, he's still going forwards. Okay, still got positive velocity, it's just starting to slow down. But if it went negative like this, then what is happening is the boy's starting off quite fast, slowing down, and then stopping here. Okay, so at this point here, they've stopped. So it's stationary for a split second, and then starts to move backwards, and he's starting to speed up as he's moving backwards, and he's just collided into the wall, and his foot's become part of it. But anything that goes below the line is a negative velocity. It's going backwards. Right. So if we have a look at this now, and have a look at which one of these is moving fastest. So we've kind of already spoken about this. The steeper the line is, the faster it's moving. If you think about what's happening, this one's covering more in the same amount of time, 10 seconds. The red line has covered more distance than the purple line. Okay, in 10 seconds covered less distance, and the green line again covered much less distance. So if we wanted to find the speed of these, we're going to need an equation, aren't we? So go back to our equations, and we wanted to find the speed, so we're going to be using this equation here, displacement, velocity and time. So we've got the distance or the displacement, got the speed or the velocity, and that's what we're wanting to find, and we know the time as well. So we rearrange that equation to speed equals distance divided by time. Alright, that should be something that you remember. That's the equation you've been doing since year 7. So, to find the speed, we need to know how much distance is covered in how much time. So all we do on the graph, I'm going to do the purple line, I'll do the middle one, and you can do the rest. I want you to do the rest of them on your booklets. So we look at the distance covered. Okay, so from there to there, the distance covered is 80 meters, and the time taken, okay, we can find as well. So I'll do that first. There's 80 meters, and the time taken was 60 seconds. So if we put that into our equation, we need to do speed equals 80 meters divided by 60 seconds. So the speed, if we do that, will give us, I really need to have a calculator next to me. Sorry about this. So the speed gives us 80 divided by 60 is 1.3 recurring. So 1.33, I will round that to meters per second. Okay, so you need to do the same thing for the green line and the red line now. Okay, so we've moved on to a velocity time graph now, and we've been given a curve, okay? And the problem with a curve is you can't just look at it and go, this is the speed straight away, okay? Or this is the acceleration. It's difficult because of the gradient is constantly changing. So you need to work out what the gradient is at a certain time. So in this case, 25 seconds, which I'll do with you, and 40 seconds, which I want you to do yourselves. So because we can't just get it normally off the graph, you are going to have to draw a tangent. This is higher tier only, by the way. So if you're watching this and you're doing foundation tier, you can ignore this bit. So what you need to do is find the point where you're looking at. So we're looking at 25 seconds, and go up to the line with your ruler, okay? And you're going to place a line that just touches, that's pretty good, the graph, okay? And I'm going to make that as big as I possibly can, just touching, so that I can find the best possible points to take my gradients from. Okay, so if you look at what I did there, when I was down here, I don't think there was many good points to take that from. When I move it up here, I think I've got a couple of good points here and here that I can take my gradient from. So I'm finding the gradient of the graph just like you normally do, because we're using now the equation, go back, acceleration is change in velocity divided by time. So I'm looking at first, what is my change in velocity? Okay, so my change in velocity, if I'm picking my points out to be here and here, I want to know how much my velocity has changed in how much time. So first off, I'll look at my change in velocity. So from there to there, it's gone from 50 to 80. Okay, so I can do that. 50 minus 80. No, I can't. 80 minus 50. Okay, means I've changed by 30 meters per second. That's how much my velocity has changed. That's my change in velocity in that certain amount of time. Right, do the same for my time. So how much is my time? How long did that take? How much has my time changed? So it's gone from 45 from 35. Okay, so again, I'm going to do 45 minus 35 equals 10 seconds. And then all I need to do is stick that into my equation, change in velocity divided by time. So I'm going to do 30 divided by 10 equals 3 meters per second squared. Okay, so 3 meters per second squared. So you need to do the same thing for 45 seconds, I think. No, sorry, 40 seconds. So look at where 40 seconds is. With your ruler, draw a gradient on. Find any 2 points where it crosses the lines. If it doesn't cross the lines perfectly, just estimate. I know the grid lines aren't perfect on here. So I might say if I pick that point there, that's between 30 and 40, I'd say that's 35. Okay. If I had to pick, I don't know, this point here and look at how many seconds that is, that's probably 21 seconds. Just estimate. This is all an estimate, by the way. It will always say, it might not say what is, it'll say estimate the acceleration. Okay, because it's not ever going to be a perfect thing. It's never going to, and it will give a range of results. Right, looking at this now, last couple of little bits. So first off, how far did the car go altogether in this thing? Okay, so this is all about using the equation displacement equals car type equals velocity times time. Okay, and using that, linking that to what we know about shapes on graphs and shapes in general. So, if I want to know how far this car's gone, I need to times the speed it's going by how long it took. So for a small example, I might just take this little box here, okay? If I want to know how far a car's gone if I do another little graph, if I say the car's gone this far, okay? That's it, that's the only distance it's travelled. It started at 7 seconds, went that speed for that long amount of time. So looking at what I've got there, I've got myself a little square. Okay, and to work out the area of that square or that rectangle, all I'm going to do is times the sides by each other. So I've got 1 meter per second for 1 second. So 1 meter per second times 1 second gives me 1 times 1 is 1. That's the distance it would have travelled. So I know then every box is actually worth 1 meter per second. So one thing I could do is just count the boxes. Okay, and if you've got a funny shape, say if on this graph, for example, if I had to estimate the distance, I'd probably work out what one box was worth and count the number of boxes and just say like those two together are probably worth like 1, maybe that one and that one are worth 1, that one and that one are worth 1, and estimate. Okay, so you can work out what 1 square is equal to and just count the squares. So if I did that, I'd be like 1, 2, 3, 4, 5, but that takes a bit of time. A different way of doing it is to split this into 2 shapes that you can recognize. So I've got a rectangle or a square here and a triangle here as well. Okay, now the height of both of these, okay, is going to be 5 meters per second. The length of the rectangle is from 3 to 8, so it's 1, 2, 3, 4, 5 seconds, and the triangle is 3 seconds, 0 to 3. So to find out the area of this rectangle here, we're going to do the 5 meters per second times 5 seconds. Okay. So that'll be 25 meters. Now because that's a rectangle, it's length times width. Now with a triangle, if I did 3 meters per second times 5 seconds, I'd actually be working out the area of this rectangle here. So from there all the way down there. Now you can see it's half of that, which works with the equation to find the area of a triangle as being half times base times height. So I need to do 3 times 5, so 5 meters per second times 3 seconds. But then I need to divide that whole thing by 2. Okay, so 3 times 5 will be 15, divided by 2 is 7.5 meters. Okay, so the whole thing together, we've travelled 7.5 meters to get to the top speed, and then 25 meters at that speed. So we add those together, 25, add 7.5, okay, that's going to give us a total of 32.5 meters travelled. Right, last little bit. So at 30 seconds on this graph, we need to look at what has happened. So if we look at what's happening, so think back to what we were talking about with the shapes of graphs. The start here is going at a constant speed, okay? So for this little bit here, just focus on this, okay? We've got a straight line, constant speed. Then it starts to go down, okay? So the speed is decreasing, so it's decelerating at this point. But at 30 seconds, something has happened. It's gone across our 0 line. So think back to our little boy with his little wall. Okay, put the wall in the middle this time. So if that's the 0, okay, sorry, the speed's 0. So moving along, he's moving at small speed and he's slowing down, and he stops at some point. Okay, and then he starts to go backwards because the velocity is now negative. If this was a distance time graph, that wouldn't just be a negative velocity, that'd be going away the opposite way from where you started. So if you had the wall in the middle, if that was a displacement time graph, that'd be getting to the wall, somehow going through it and going backwards from there. But in a velocity time graph, all it means is you're starting to go backwards, starting to go back towards where you went, okay? And then you're kind of accelerating backwards because your velocity is going up. Negative 30 is still a high velocity, it's getting faster, but it's going backwards. So negative and positive just tell you which way something is going. So 30 seconds, if you look, the direction has changed. So it's gone from a positive velocity to a negative velocity, which just means whatever this is, probably a car, because 30 meters per second is about a car's speed, that's changed direction. So you should now have the ability to fill in all of that booklet. So some of these things you will have to do yourself, like I've shown you how to do the acceleration using a tangent, so you need to do the other one. Showing you how to find the speed, so you need to, again, do the other two. So you should be able to hand me back in now the booklet full of notes, showing me what revision you've done for this.